So we're going to take a look at section 10.3, and this is about mathematical modeling. And the idea is that some relationships in the real world can be represented with lines. Now, to do that, we want a little more flexibility in how we construct lines. Now, we've seen how to construct lines when we know a slope and a y-intercept. So if we know something like this, a little more in there like that. And this right here, y-intercept 0b. And then let's say this has a slope of m with a run. And in this case, your rise is going to be negative. It's a fall. So whenever you have a line dropping, you have a negative rise. And again, that's the same as a fall. So with that, we can come up with a line y equals mx plus b. And that would be the equation for this line. Now, to get something a little more flexible is we're going to want to be able to find the equation of a line without having to have the point that we know be the y-intercept. So let's take a look, and pardon me for just a moment. Get a little eraser here. Something will act as an eraser. All right. So we're going to do something like this. Let's say we have our line, and it's got a slope m. And there's this some point, x1, y1. And we want to construct an equation for this line with this information. So the way we do this, let's pick some point randomly on this line. Say this one. It's kind of a generic point. We don't know exactly, well, I mean, we put it on the line, but we could have put this here, 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 or here. And just for visual purposes, I'm going to say put it here, but this could actually appear anywhere on this line. And because it can appear anywhere on this line, this x could be pretty much any number along the x-axis, and this y, well, it needs to be a y that corresponds with this x, according to the formula of the line. If only we knew what it was. But there is a relationship between these two. That's that formula. But clearly we don't have actual numbers here. Now, when we get these kinds of problems, these would actually be numbers, and that would actually be a number too, or number also. So, as is the case with lines, the slope between any 2 points is always going to be the same. So the slope between these 2 points will be the same as if we took the slope between this point and a point here, or this point down there. You're always going to get the same slope. So let's say this is, let's give these a little identity. Say this is, call this x2 and y2, even though we wouldn't be given these as numbers. Again, those are the only numbers we'd be given. So slope is y2 minus y1, x2 minus x1, and we fill things in. So y2 is just y, x2 is just x. And what we're going to do, we're going to kind of solve for y. We're actually just going to solve for y minus y1. So to do that, we'll multiply both sides by x minus x1. And the reason we do that since we're dividing by x minus x1, we want to do the opposite of dividing by that. And the opposite of division is multiplication. Just like the opposite of addition is subtraction. So let's multiply by x minus x1. So that means when we do the opposite, things cancel. But because of this equal sign, what we do to one side, we have to do to the other. So I'm going to rewrite this as m x minus x1 equals y minus y1. With multiplication, order doesn't matter. So this times that is the same as that times this. So I have that times this. And we typically write this in a slightly different form. And that's the form. It's called the point-slope formula. Point, slope. It's different than the slope-intercept form because, in this case, this point could be much more generic than an intercept. It doesn't have to be on the y-axis. And there we go. So, well, we use this. There's two typical problems we get with this that aren't applications. First off, we might get something like this. I have a line with a slope of 2, and we'll be given a point of, say, 3, -1. And we want to find the equation of a line with this slope, but passing through that point. So what we do, we already have our m. Again, let's call this x1, call that y1. So we take our point slope formula, and we plug in those numbers. Double negative becomes a positive. We can distribute the two. And we get 2x minus 6. Finally, subtract 1 from both sides. And what you're going to notice with this, we're going to try to keep it in slope-intercept form anyway. So even though we're working with this point-slope formula, we're going to put it in slope-intercept form. It's just sort of the standard practice in mathematics. We get y is 2x minus 7. And that is the answer. So that's one type of problem you're going to get with this. And then there's a more challenging one. Let's say we were asked to do this. Now, in this case, we're given 2 points and we're not given a slope. All the lines that we've tried to find, it's always a point with a slope. Well, now I got a situation where they didn't give us the slope, but actually they did. You see, if we have 2 points, we can use our slope formula to find the slope of a line passing through those 2 points. And then once we have that slope, well, then we have a slope we can use for our point slope formula. So let's label these, and this is our first point, so I'll call this x1, y1. Second point, x2, y2. And now we use our slope formula. So we fill in the numbers. That's -4, -4, and that comes out to +1. Negative divided by negative is a positive, or simply put, the same number divided by itself and gives you 1, with the exception of 0. Again, 0 divided by 0 is undefined. But other numbers than 0, that number divided by itself is 1. So we've got our slope. Now we can use our point slope formula. Now, what I'm going to do, we know m is 1 now. We could use x1 and y1, because they're right there. That's perfectly fine. If you wanted to, you could use x2 and y2. So m will always be 1 regardless, at least in this particular example, because we found out the slope between these 2 points is 1. I should say, if these were different points, the slope could have turned out to be 2, or the slope could have been -1/2. But in this case, the slope turned out to be 1. So this will be 1 for this problem, but it'll be 1 whether we use x1 and y1 or x2 and y2. It'll still be 1. And you could do that, but I'm going to stick with x1, y1 because it's just easier to go with these labels. They're already there. They're sort of screaming at us. Use us, and so we'll do that. We'll plug those in. Well, 1 times anything, that doesn't change anything. Add 1 to both sides. And that's it. That's your answer. So that's how you can find the line passing through 2 points. You calculate the slope, whatever slope that turns out to be. In this question, it came out to 1, but it could turn out to be something else in a different problem. And then use one of these points as x1 and y1, or you could use x2 and y2, and then solve for y as before, and that gives you your formula. Now, the next thing to look at is applications. And let's see. So oftentimes in the applications problems, they want you to identify 2 points. Input, output, input, output. And using those 2 points, you're going to do exactly what we did with this most recent example. We'll use the 2 points to find the slope. We'll choose one of the points to be x1, y1, and then we'll solve for the formula that represents what's going on in the problem. And then oftentimes what they'll have you do is once you get your formula, they'll want you to put it to work. Answer some question, like predict what will be the amount of sales if there are so many cars available or something. So we're going to look at something a little different. What would be the number of cars sold? If, well, sort of similar. If the prices were different, how does price affect car sales? So here's a problem. Let's say we have this. Excuse pardon me. A manufacturer of economy cars, and this is the data they give us. Sales are 50,000 cars for, let's see the price that they asked for, $18,000 per car. So if the cars are $18,000 a piece, they're going to sell 50,000 of them. And let's see, a time frame apparently is a month. So now let's say we lower that price. What it turns out to be is 55,000. That's sold your cars are 17,500 each. So when the cars are 18,000, you're going to sell 50,000 of these in a month. But if you lower the price to 17,500, you're going to sell more cars, 55,000. So here's the grand question. How many cars predict? How many? How many cars will be sold for 17,000 each? So what do we do here? Now, there's a little subtlety with this problem, because to predict the number of cars, before we deal with this, we got to get a formula. So it might seem like, well, they're asking us to predict, so if you look at this, look at this, look at this, look at this, and sort of try to, you might be able to visualize it, you could. But oftentimes for us, what we're going to do, this is going to come later. We need to almost automatically just look for a formula. So what can we do? Well, let's take a look at this. We want to think in terms of cause and effect, input and output. We have 2 points. There's 50,000, 18,000. Second point, 50,000, 17,500. These two go together, these two go together. What we need to figure out is, say for this point, and this one also, is the number of cars the input, or is that the output? Is the price the input, or is the price the output? And we want to think about this in terms of cause and effect. Is something causing something else? So is the price causing the number of cars sold to change? So if we change price, does that lead to a change in the number of cars sold? Or is what's happening is when you change the number of cars sold, that's changing the price? Now, it depends what you envision in terms of human agency. For example, there could be someone who's watching the number of cars sold and who's, okay, we're going to adjust the price, we're going to adjust the price. But there's sort of a, I guess you call Occam's razor approach to this, where we're trying to have this less, not so much human agency. Maybe they might say that it's okay to have that in some problems. But what we're going to look for is a very simple cause and effect. If you just set the price and just walk away, the number of cars will just kind of sort itself out. So it seems, using that approach, that we could say the price is the input. We set the price first, and then the effect is the number of cars that we sell. We set the price, that's the cause. The effect is the number of cars. So that means the cause will be the input, the effect will be the output. And so that means price is input, effect is output. And again, depending on how the problem is worded or what they're asking for, maybe you do switch those two around. But in this case, it seems reasonable and simpler just to go with set the price and then figure out the output, the number of cars. The other way you could kind of tell which should be input and output is that question they asked at the end. Predict the number of cars we're going to sell if we sell them for 17,000 each. That means we start with the 17,000 and then we're wondering what the effect is. So that also kind of tells us what is the cause and effect. We're going to start with the cause, we'll end with the effect. The question they asked us to do was predict the number of cars sold given that we set a price first, 17,000. So that seems to suggest that the dollar amount is the input, the number of cars is the output. So going with that, 18,000 and 50,000. Then we had 17,500, 55,000. So I'm going to call these, and again, these are 2 points. So we want to find a line passing through these 2 points. That's the formula we want. So we'll call this one x1, y1, x2, y2. And so we want to come up with the formula that for the line passing through these 2 points. And then once we have that formula, we can put an input of 17,000 and figure out the output for that input. So first off, we need a slope. So y2 minus y1. And then x2 minus x1. We get a slope of -10. Now, that actually makes sense if you kind of think about it. If we think of price, since we're going to call price our input or the x values, so price means, well, that means that price is on the x-axis, and that means the number of cars is the y-axis. So as we increase the price, say we go from here to here, the number of cars shrinks from here to here. So that means as you go in this direction of increasing price, the number of cars should be decreasing. So that sort of suggests a negative slope. So anyway, well, it does suggest a negative slope. So we have our slope of -10, and I'm just going to use x1 and y1, which were 18,000 and 50,000. So we got to distribute this -10. This will become negative times negative is positive, plus 180,000. 18,000 times 10 is 180,000. And then we could add 5,000 to both sides. or 50,000 rather. And here is our formula. So this tells us if we put in a price X, what we'll get as an output is the number of cars Y. Price, number of cars. So this is what they asked us to do. Predict the number of cars we're going to sell when the price is 17,000. So to do that, replace X with 17,000. So what we've noticed is as we lower the price, the number of cars goes up. So for $18,000, we sold 50,000 cars. $17,500, we sold 55,000 cars. 17,000, we should sell more cars. In other words, we're going backwards along the x-axis. And sure enough, we get 60,000. And that's going to be our answer. So to kind of illustrate what was going on, graphically what we had is cars and price, and our line's doing this. Here, this is the y-intercept of 0, 230,000. And so as the price increases, the number of cars decreases. But as the price goes backwards, it gets smaller and smaller, the number of cars is going to increase. And so that's what we've seen. As we drop the price from 18,000 to 17,000, we go from selling 50,000 cars at 18,000, say like this. We sell 50K cars, but at 17,000, we're selling 60K cars. And so that's what's going on with our mathematical model. So that's really it for 10.3. If you have any questions, let me know. I'll take a quick flip through here, make sure there's nothing else really. Yeah, that's it. If you have any questions, let me know. And the only thing I'll mention real quick, there is a type of problem where they'll give you a number of data, like they'll give you something like this. So mention this real quick. You'll get some problems that they'll have some X values and Y values, and they'll want you to construct a model using those. what they'll usually tell you to do is use 2 points. Say this one and this one. These actually are points. X value, Y value. X value, Y value. So what you get X1, Y1, X2, Y2. And then using these points, come up with a line that passes through them. Again, using your slope formula. And then once you get a slope, you can use a point in your point slope formula to come up with the formula for the line. And that's it. So if any questions, let me know. Other than that, have a wonderful evening.